used for this demo. So first of all, we are very excited to have the opportunity to partner with Rivian this year and explore setting up their R1T inside of the Unreal Engine. We decided to use this as an opportunity to highlight some of the features in our vehicle system, our fluid system, and a new tetrahedral solver that models volumetric soft body dynamics. So first up is our vehicle system. The Chaos Vehicle plugin was utilized during the city sample demo for the destructible vehicles system and has been available within the engine since release 5.0. This version of our vehicle system allows for skeletal mesh-based vehicle setups, where we perform scene queries from wheel positions to emulate the suspension characteristics of a vehicle. And we also provide a torque model to help recreate a typical transmission-based drivetrain. So for this demo, one of our first additions was that we needed to add the ability to emulate the Rivian drivetrain, where each wheel has its own electric motor. So specifications regarding the torque and energy distribution of the Rivian's R1T electric motors was directly discussed with Rivian engineers. Our current system provides a maximum torque that is divided between all the active wheels of the simulation. However, for a Rivian, each wheel is computer controlled, and the energy is directed to the necessary wheel based on its interaction with the environment. For example, the wheel with the highest coefficient of friction will be given the most power, and it can provide the best traction for the vehicle. This means that the wheel motion for the Rivian's drivetrain is much more precise than a standard vehicle model. So for this demo, our goal was to model the rock crawl mode of the Rivian. This means that the throttle input was reduced to limit the full power of the electric motors. The torque curve was cut after 20 miles an hour. And acceleration was limited to emulate the feeling of a four-wheel drive's low gear setting. Now, keep in mind, the Rivian doesn't actually have a low gear, but it feels like that when you drive it in this rock crawl mode. It moves very slowly with a precise motion over a tough terrain. We used the existing engine braking parameters to simulate the effect of the motor's regenerative braking system. We set the transmission to have one forward gear and experimented with finding an underlying gear ratio within our vehicle that matched that of Rivian's. Resistance values were tuned in the interface to make the vehicle quickly deaccelerate when the throttle is not applied, which aids in the controllability when driving a downhill. But again, it was just more to emulate this four-wheel drive setting for the crawl mode. So the adjustment of the throttle and the braking parameters were all managed through our existing controls in the vehicle system. However, the Rivian's R1T had a few features that were not completely represented in the plugin, and we needed to add them. The most obvious differences were the wheel spin characteristics and the complex behavior of the R1T's dynamic suspension. So first, Rivian prides themselves on their ability to not over-rotate a wheel or slip or spin out a tire. Our simulation already had traction control, but we added a maximum spin threshold, which prevents the wheel from rotating too quickly when it's off the ground. Rivian indicated that the wheel will just slowly turn until it finds the ground again, and we incorporated that behavior into our model. The different drive modes advertised by Rivian will allow the drivers to control the height of the vehicle from the in-vehicle display. The rock crawl mode will raise the vehicle to 15 inches above the ground, while the sport mode will reduce its height to 9 inches. To emulate Rivian's ability to transition between the different drive modes, a new function was exposed to blueprints that allows artists to modify the suspension height of the vehicle at runtime. Considering the pace of the demo, only rock crawl and all-purpose mode were modeled for our asset, and sadly, the 0 to 60 in 3 seconds for the sport mode was not. So no driving game today, or racing game today, sorry. So let's transition now and talk about the Niagara fluid system. The water feature you saw in the demo was a real-time fluid simulation authored within Engine. The Unreal Engine's Niagara-based fluid system was released in Engine version 5.0 and offers artists and end users interactive, real-time water simulations. The toolset is fully incorporated within Niagara and controllable using standard gameplay setups. Over the past year, updates have been added that improve upon the system's capabilities and workflows. The Niagara fluid system supports a 2D and 3D gas and water simulation. With the interface completely built within Niagara, the artists are encouraged to explore the feature set inspecting our predefined template workflows, and mixing and matching features to achieve a desired look. As an artist, you are encouraged to tinker. As an engineer, you are encouraged to learn from our source and contribute through GitHub if interested. Niagara's tools provide several levels of abstraction for an artist when building setups and workflows. Here we see on the left an example of an emitter's summary view, which provides high-level simulation controls that simplifies an artist's interaction with the fluid system. However, as an expert user that needs a more fine-grained level of control, the emitter's underlying implementation is still available to expose all aspects of a complex effect. That's on the right. Artists will interact with the fluid system using engine blueprints. As you can imagine, blueprints provide artists with gameplay controls over the real-time environment, allowing for event triggers that can start and stop a simulation, control collision interactions, allow artistic direction using fields, and direct the fluids with velocities. Of course, if real-time is not your thing, and you need to utilize a more traditional visual effects pipeline for cinematic-based workflows, you can cache your simulation results and play them back within Sequencer. So for this example, we are running a live sim in Sequencer with a keyframe controller. We adjust the collider's timing to get the desired look, and then cache the fluid sim with a simple button on the cache track. We can then scrub the results or render using the cache, thus avoiding a heavy simulation every time we need to render the results. The liquid solver is based on the fluid implicit particle method, also known as FLIP. The solver simulates water particles moving through a voxel grid that defines pressures from the velocities of the particles. To represent interactions with the environments, collisions are stored as boundary conditions within the grid and prevent the flow of particles through scene geometry. Ultimately, the FLIP solver produces a velocity that gives a plausible, divergent-free motion, which can then be transferred from the simulation grid back onto the particles. Finally, to visualize the results of the simulation, the particles are stamped into a sign distance field so that a surface volume can be generated for rendering. The sign distance field is then smoothed to reduce noise artifacts introduced by the rasterization of the particles on the grid. Once the simulation is complete, surface particles and secondary effects like wet maps can be layered on top of the simulation results to add to the next level of realism. Here we see an example of a secondary particle adding a whitewater effect to the surface of the fluid. Also, within the demo, you will see trails of water that are left from the tires as the vehicle leaves the pond. To integrate this fluid setup into the Rivian demo, our artists first pre-computed the ground sign distance field that produced a watertight cup for the fluid particles. The Rivian was represented using mesh distance fields that pushed the water away from the vehicle. Also, the initial state of the pond needed to be still and glossy to kind of indicate the untouched nature of the surface. To keep the fluid in a perfectly still state, a trigger volume was created to freeze the velocity from within the blueprint. Similar trigger volumes were also utilized to hide the simulation when not visible, saving valuable resources on the GPU. Another aspect of bringing a bit more realism into this demo involved modeling the interactions of the tires with the environment. We utilized a tetrahedral simulation to model the deformations of the tires as it interacts with the terrain. This is a real-time simulation that constantly adjusts the relative volumes of the tetrahedron as it interacts with the environment and is gameplay directable through the use of animation constraints. The Chaos Tetrahedral Solver offers a stable, real-time simulation framework for the evaluation of volume-preserving lattices. One of the benefits of this solver is that it effectively gives us a dial to control accuracy versus speed depending on your target application. This is a CPU-based simulation, which is advantageous for several reasons. Rendering resources on the GPU can consume a significant amount of hardware budget due to the resolution of the geometry in the environment or the fluids or whatever you have going on the GPU. And also, having access to the deformable simulation on the CPU allows us to start exploring deformable models as gameplay affecting elements. For the Rivian simulation, we were targeting speed. The results needed to run on a reasonably high-end PC and remain stable and artifact-free. which can be quite a challenge for dynamics across volumetric meshes. For example, the density of the mesh, or just the number of connections across the mesh, can dictate the iteration requirements of the solver. As a result, a denser mesh will require higher iteration counts to properly propagate the energy through the system. Therefore, a balance needs to be found that allows the mesh to remain visibly plausible but performant and within budget. So I intentionally added this bottom video to make a point about convergence and mesh resolution. The noise artifacts we see on the lower example are an indicator that the simulator is not taking enough iterations and will need more time to resolve. Unfortunately, this means that you will not be able to run at this level of detail in real time and will need to consider reducing your resolution. If you actually need this level of detail in your simulation, you will need to consider our in-engine cached solution to get reasonable results and then potentially play back a cached canned animation inside the simulator or inside your game. Okay, so the tire's simulation geometry is modeled using a radial tetrahedral mesh. We experimented with different radial meshing techniques to help explore the bending characteristics of the tire. In this example, we are testing an isosurface stuffing tetrahedralization from Tetwild, which will be released in 5.2, along with a radial tetrahedralization algorithm developed for the demo. By varying the structure and density of the mesh, by varying the structure and density of the mesh, we can see that the simulation will produce dramatically different results. And we use those results to help configure the iteration requirements of the solver. The tetrahedral asset that drives the tire's geometry is also configured using an evaluated node graph, which assists in the procedural authoring of simulation setups. So the vertices of the tetrahedron along the wheel's rim are constrained using kinematic constraints, also known as infinite mass attachments. The constrained vertices will follow the rotational animation of the axle produced by the vehicle system as the player drives around. The connected tetrahedron that are not constrained by the animation are then carried along for the ride. And while the tire was affixed to the wheel using kinematics, the interaction with the environment was accomplished using raycasts through vertices along the surface of the wheel. The raycasts provide contact information at user-specified control points that then push the surface of the tire out of the ground geometry. This setup allows artists to configure the accuracy of the tire's interaction with its environment and also tune the resolution of the collision response based on CPU limitations. Collision interactions against dynamic geometry were also added using convex and analytic collision objects along the path of the demo. The vehicle will stream dynamic geometry into and out of the solver based on the proximity to the wheels. Here we can see the tires interacting with the dynamic rigid bodies as the vehicle drives through the environment. Lastly, to see the results of the simulation, we transfer the simulation mesh onto a higher resolution surface for render. This approach can target both nanite and skeletal mesh geometry types. For the Rivian, we are using texture maps to deform the nanite geometry. However, skeletal mesh deformations can be accomplished through an Optimus deformer as well. And I want to just pause here for a second and express how impressed I am with what the rendering team has been able to accomplish. This tire is roughly 1 million vertices, which is a very high resolution for a deformable gameplay asset. Being able to push the deformations into such a high resolution surface has really helped sell the realism of the tire. So the Rivian is just one example of how you could perform a deformable simulation in engine. Because the solver we are using allows for convergence if you allow it to take enough time, you can also use our solver to produce cached, high-resolution simulations that can be played back within Sequencer. For example, this shows a multi-layered muscular skeletal simulation where the underlying muscles are simulated against the skeleton. On the left, we have a passive muscle simulation of a character against its animation. On the right, we see a fascia layer simulated on top of the muscles. Sorry, that first frame did not play. So please note, this example is not a real-time simulation and is experimental in 5.2. but it could be used in a character training pipeline to construct an ML-based GPU deformer if you want a real-time solution on the skin. So if you would like more information about our ML-based character simulation pipeline, please see our 2 o'clock talk, Metahumans, Framework, and Machine Learning for Next-Gen Character Deformations. So lastly, here's another look at the different elements coming together. The vehicle constraints, the fluid system, the deformable tires, all simulating in real time. Everything that we have shown here is available in the 5.2 release. Details for the Chaos tetrahedral simulation will be posted on the Community Learning channel in the coming days, alongside the existing documentation for the Chaos vehicle plugin and the Niagara fluid system. And I also want to give a big thanks to the Chaos simulation team. It has been a tremendous amount of work to get us to a point where we can show these type of simulations, and we are all very excited to show the world what we can do. So please come by the booth if you have any questions. And now I'd like to introduce Marion, who will be talking about our new material authoring system. Thank you.
Thank you, sir. All right. Hello, everyone. My name is Marian Alaoui. I'm technical artist for Epic Games, part of the Special Project team. Today, I'm really honored to present you Substrate, the new layering system for Unreal Engine 5. The beautiful jungle demo called Electric Dreams demonstrates this new powerful feature that improves a lot the visual fidelity. All materials in this demo are using this new material system by simply enabling the option in the project settings. But now, let's talk about what is Substrate and how is it working. Before going in the details, it is important to understand one of the core features. In traditional real-time rendering, reflection is calculated by merging all the parameters all together to output a final specular that's going to be more or less accurate. With this new system, Unreal is able to separate each reflection for each layer by calculating them separately, and that's going to output the result for you. With this in mind, artists will be able to work with accurate material based on an optimized multi-specular, also called multi-BSDF, that will increase the visual possibilities. By upgrading the new material graph, Unreal is offering more flexibility with less complexity by merging multiple shading models into a single node. Default lit, subsurface, skin, and fuzz would be all merged together. Each layer in Substrate are composed by an interface, here in yellow, and a medium in blue. Substrate helps to reason about what we manipulate and how light would interact when dealing with those properties. Every node we are playing with are allowing physically accurate transition, but still allowing artists to do some variation and explore different art styles. Each substrate element will generate a spatial topology, allowing the engine to easily reorder the layering system. Substrate is coming with a new node called Slab that offers a lot of advantages. With parameters, you can create a huge variety of materials that could combine different shading models into a single asset. Each BSDF is represented as matter, where stacking them together is resulting in a variable list of packed bytes that will change based on the complexity of the material. You can compare this topology of the system to a G-buffer, for example. This adaptive storage enables per pixel topology and features scalability that provides a range of optimization without sacrificing the quality. This is one of the key elements of Substrate. Don't lerp anymore, just use Substrate operators. The new layering system allows you to physically transition between matters such as dielectric and conductors. Parametric blending is allowing per layer optimization that gives you freedom to choose between performance and quality. Note that this is going to be inside the different operators I'm going to show you just after. Substrate is offering you two main types of composition. Horizontal, that will mix the two slabs on the same depth, computing both specular individually to mesh them together. And the vertical composition that take into account the thickness or the depth of the top layer to apply transmittance and proper absorption based on your inputs. Finally, the wet coverage node that is working similarly to an opacity layer, where you will be able to change the opacity of a specific slab that is also working per pixel. This is very useful, as you could remove the entire slab from the material evaluation when the coverage is set to 0. If your project is currently using the old material system and you would like to upgrade to substrates, you will be able to use the Substrate legacy conversion that allows you to automatically make your old material compatible with Substrate. When enabling the option, all materials will be automatically converted using that node. You don't need to do any kind of manual work for this. But now that we covered the theory, let's go for a few examples that's going to be better. One of the best updates is giving the opportunity to transition between dielectric to metallic, for example. In this video, you can see the nice transition between the two types of matter. By calculating two separate BSDF, Substrate will render the transition with accuracy. On the right, you can see the material graph composed by a horizontal layer blended with a mass texture. This example is a bit different, as you can see. Substrate is now allowing artists to play with the F0 and F90 values. This new functionality increases the possibilities by keeping the results physically correct. The F0 and F90 has been added to the slab to facilitate the control. Here, you can see the simplicity of the material graph by simply giving the two colors directly to the nodes. We also extend the possibility by adding a thin layer node. This is representing a layer of matter, that absorbs part of the light and allowing you to see these very nice chromatic effects. You will be able to play with the various parameters, such as IOR, normal, and thickness to vary the results. It is important to keep in mind that this approximation is based on the view angle only. By upgrading our new shading model, we are now supporting the second roughness as a default feature in Substrate. This will give you more control over the shape of the tail for the specular by just creating a new node called haziness. This is going to simplify the work a lot for you. The first model has been also improved a lot. The artists will be able to have more flexibility and will be able to work way better with this new shading model updates. Simulating the fuzz with improved physical representation will make your material more natural than ever. The rough refraction is a new feature implemented in Substrate to facilitate the process of creating rough layer by blurring the bottom layer for the opaque material, for example. But here, as you can see, this option is also working with translucent material by blurring the scene color based on the depth. With this option, you don't need to do any custom tricks anymore. This is just working. All right, now that we covered some simple example, I would like you to go for a more complex one. We're gonna rebuild together the nice op-roll effect we used in the Electric Dreams demo you saw just before. In the first place, we will create the bottom layer representing the back of the element. To increase the depth filling, we will create a fake refraction effect that's going to be based on normal and the view angle by changing the specular. For this, we will play with the F0 and the F90 we just saw before. In order to decrease the strong contrast of the specular highlights, we will use the new haziness node to grow the tail in order to affect the reflection. The middle layer is a bit more complex. The idea is to add these nice chromatic effects created by the topology of the piece. We will first generate the parallax occlusion to simulate the 3D model inside the material. Then, by reading the depth saved in the texture, we can sample the material information directly inside the vertical layer. It is important to imagine this layer as a translucent matter that absorbs a certain range of the light in order to reveal the bottom layer. An additional anisotropy effect is used to break this linear reflection, giving a more natural look by playing with the tangent, for example. By adding a coating layer, we will increase the depth of the parallax effects. The clear coat, similarly to the previous example, will also use the substrate transmittance mean-free path that simplify the mathematical representation of the transmittance, giving us the opportunity to output the final color based on the thickness or the depth. You could imagine this coating has a thick piece of tinted resin, for example, that have been polished. Finally, let's add some dust onto this multi-layer material. By simply adding another vertical composition node, we can properly generate and calculate all those complex BSDF that are all very different. One of the advantages of substrates is the possibility to split each group of matter as an individual pieces on your graph, which gives the artist a clean material asset, which is very important. You can also use material function to clean your work in order to help the readability of the material. All right, with all those effects, you will need to control the performance impact of your creativity. To help artists and engineers to have some feedback, Substrate is coming with different tools to dig inside this layering system. Various view modes have been added to track your material complexity. As you know, stacking multiple BSDF could be expensive if you're not too careful. However, Substrate will help you to find the best combination between performance and quality. The first view mode is showing the number of BSDF you have per pixel. By simply looking at the colors, you will be able to approve the usage of extra layers in your material based on your target quality. It is a very simple view mode, but it's very useful and could save you a ton of time. The second image is showing an in-depth layers or an in-depth information on your different layers. You will be able to inspect each element, such as roughness, diffuse color, and minimal values. By hovering the material with your cursor, a 3D gizmo will help you to analyze each normal of your material. An additional information will be added to the screen in order to visualize the performance impact on your memory. That is very important to keep in mind. The last image is an example of many advanced view modes you have in Substrate. However, this requires to be enabled in the project setting. This UI is helping to inspect each layer and understanding how Substrate is reading your material. This advanced debugger is heavy on the performance and needs to be disabled if you are targeting for performance. It is important to note that the current system do have some limitation. This experimental feature is currently allowing the artist to have a maximum of 8 slabs, as well as a limited number of tangent space in your material. All right, so what is next? Substrate is currently not supported by the path tracer, but the team is working really hard to have it working properly. We would like you to still use both options in order to validate your result with the path tracer. As you know, a continuous effort is made by the developer to always improve the performance without losing the quality of your material. Both performance and optimization are in the radar of the engineering team. We are also trying to be listening for feedbacks in order to improve the stability of Substrate. All right. If you have any question, feel free to see us directly at the booth or attend to the session that's going to be also happening at the booth today. I would like to do a special thank you to the rendering team, especially to Sébastien Hillier and Charles de Rossier, who has been amazing creating this amazing framework. With all this in mind, I would like to thank you and enjoy the rest of the day.